Okay, so this is a pre-lab video to kind of help you through the lab for digital logic devices. What you're looking at right there is what is called an integrated circuit. It's called a DIP package, which stands for dual inline package or dual inline pin. So you can see there are two sets of rows of pins. And the important thing is when you're plugging it into the breadboard, it has to kind of straddle the center of the breadboard. The reason for that is this dividing line in the center basically isolates the top half from the bottom half connections. If you accidentally plugged it into the top part, it would short the pins. So we want every one of these pins to be isolated. Now, some important things about this device. It actually has 6 individual inverters in it. And if you want to kind of see what a typical schematic symbol for an inverter, it looks like this. So pin 1 is the input, pin 2 is the output, and then pins 14 and 7 are the power and ground pins. And we'll come back to this schematic in a second. But the important thing is that there's not just one device in that package, there are actually 6 of them. And that's kind of shown in the video, or rather in the lab report handout. So if you looked at the inside of this device, you'd have something that looks like this, where you have pin 1, pin 2, 3, 4, running out of space here, got to plan ahead, and then pins 5 and 6, and then pin 7 is ground. Sorry about that. Let's bring this up a little bit so you can see what I'm drawing there. Okay, so that's the package, what that first part of the package looks like. And then on the other side, so this is pin 7 here, which is connected to ground. The way that this continues then is at pins 9 and 8, 8 is this other corner here, and then pin 9, drawing it on the outside now, is the other side of that other inverter. So you end up with 6 of these, and then pin 14 on the top left is your plus 5 volts. And as I mentioned before, 7 is ground. So they're actually, let's go ahead and finish drawing this out here, I guess. We have pin 11 and 10, and then 13 and 12. So a couple things that are important to remember when you're looking at this package is that the pins start in the bottom left corner, but then go around kind of in a circle here. A common mistake is people think it goes from pin 1 to 7 and then 8 to 14, but it goes in a loop. The other thing that's very important is that trying to identify where pin 1 is, there's usually a notch at that end or a dot here. But more often than not, also the actual text that's written on the package is usually in that orientation. Now, I tried to make this a little bit easier for you so that when you actually look at the package here, I already labeled it in the proper orientation. But let's kind of zoom in a little bit and take a look at this device and look at what you can actually see on the front of it, or the top of it. Okay, so there you can see the little notch at that end, and so that indicates that pin 1 is right there. Okay, so let's take a look at the lab and how we're going to wire up this first circuit. Now, because it's very easy to forget the power pins, because a lot of the times you're kind of fixated on all the logic gate connections, we want to wire the power pins first. So I'm going to go to pin 7 here and connect it to ground. And I'm going to go to pin 14 up on the top left corner and wire it to the positive supply. Okay. Now, sometimes these devices have 16 pins. There's some that have 20. Sometimes they're 8 pins. But the same orientation is always the case. It starts at 1 and loops around to the highest number at the end. The other thing, too, you don't want to wire these when the breadboard is powered up. So make sure that the breadboard is not powered and wire up the circuit. So let's take a look at the rest of the circuit here. Okay, so I'm also going to make sure as I do the schematic that I mark off the connections as I go, just like you did for the relay labs and other labs. So I'm going to just put a little dash there and a dash there, If you want to highlight the line, that's fine too. That just shows I've connected those pins. So let's see, why don't we go with a switch to start with. I'm going to put the switch over here, plug it in there, and I'm going to take the input pin. If we take a look, the 5 volts goes directly to that side of the switch. So I'll wire that up. 5 volts. And the other side goes to 2 places. It goes to pin 1 on the device. So I'll connect that to pin 1. Okay. But also there's a resistor there. Now the reason that resistor there is that these devices have what's called a very high impedance, or a very high input resistance. And it takes hardly any current to turn on the device. Picoamps even, just tiny, tiny amounts of current. So if we don't establish a base current, if that switch is not pressed, if that input was floating and it wasn't connected to the resistor, it'd be floating and it could actually turn on or off depending on how much current is literally in the air around it, or if you touched it with your finger. So the purpose of this resistor is to allow a small amount of current to flow to ground to kind of establish it at a base value. Now, it shows that it's connected to the switch to pin 1. I'm going to just wire it directly from pin 1 to ground there. So I could have wired it up over here. Whoops, and I'm off by 1, sorry. It's always hard to try to do this on the video at the same time. Sorry about that. I could have run the wire over here to ground at the end of the switch there, but since it's all connected together, I just connected it to pin 1 on the inverter input there. Okay, so that's the input to the switch. If I left that off, I'll show you what happens if you're not careful with that. Now, on the output, we're going to, from pin 2, let me mark those off. So the output, we're going to go from pin 2, and because I want to leave a little bit of space, I'm going to use a jumper here. And then that goes to a 330 ohm resistor. I've just got a 1K. I'm just going to use that for now because I know it'll probably work. But you can use a 330 ohm. And then I'm going to take my LED and connect the positive end, which is the anode, which is the longer lead, to that resistor. And the other side, I'm going to go to ground, like that, across those 2 points there. Okay, so that's the complete circuit. So let's go ahead and test this and see what happens. But before we do that, let's see if we can kind of see what we're going to expect to have happen. If the switch isn't pressed, that input is pulled to ground. And that would be representative of a 0 or a logic low input to the gate. And again, this is kind of weird. You look at this symbol, it looks nothing like the package. But this symbol is used, that's the common way of representing the actual inverter. So if we don't press the switch, it's pulled low, but it's inverting the output, so we'd expect this to go to 1 or 5 volts and turn on the LED. Now in the opposite situation, if that switch is pressed, that input would go to 1 or 5 volts because there's a lot more current flowing through that switch than is going through the small resistor. And the output is inverted, so we'd expect that output to be 0. And there'd be no, since we have 0 volts and 0 volts here, there'd be no current flowing through the LED. So let's go ahead and test the circuit and see what happens. Okay, I'm going to turn on my little power supply here, which is different than your power supply that you have. And you'll see that the output is high, which is what we're expecting. The switch is not pressed. We have a low on the input and a high on the output. If we press a switch, the logic level changes. Now part of this lab is measuring the voltage at the output pin, pin 2, right there on the resistor, to ground with a meter to see what the actual output voltages are. Okay, that's the first lab The other part of the lab is very similar. We're going to be using a 7408 or 7432. Those are AND gates and OR gates. The difference there is that we'll use 2 switches instead of 1. The nice thing is that you can just substitute, it's the same layout of the gates inside the package, so you don't need to rewire the whole circuit. When you're done testing the first one, unplug it, plug the other IC in, and you should be good to go.